This video will cover section 5.5, Greatest Common Factor and Factoring by Grouping for Math 95 at LBCC. Our goals for this section are to identify the greatest common factor, which we often abbreviate as the GCF, to factor out the greatest common factor, and to factor by grouping. For most of the rest of this chapter, we will be learning how to factor. That is, we'll be learning to take polynomial expressions and rewrite them as a product of factors rather than as a sum of terms. Essentially, we will be unmultiplying. In preparation for that, we should remember what the difference is between factors and terms. Factors are things that are being multiplied together, while terms are things that are being added together. For example, in 2x squared y, the factors are 2, x, x, and y. In 2x squared plus 7x plus 2, the terms are 2x squared, 7x, and 2. The purpose of all this factoring that we're going to do isn't going to become clear for a little while, but eventually we're going to be able to use factoring to solve polynomial equations. Polynomial equations show up in all kinds of awesome applications, especially physics. To get started with factoring, we need to start by learning to identify the greatest common factor in two terms. We're going to start with a numerical example though, something you might be more familiar with. What is the greatest common factor of 56 and 42? What we mean by that is, what is the biggest number that goes into both 56 and 42? You may be able to find the greatest common factor by guess and check, but I'm going to show you a systematic method for finding the greatest common factor. And it starts with finding the prime factorization of our two numbers. I'll start by finding the factor tree for 56. 56 is 8 multiplied by 7. Now 7's prime, so it doesn't break down anymore, but 8 can be broken down into 2 times 4. And finally, 4 can be broken down into 2 times 2. Now at the ends of my branches, I don't have any more numbers that can be broken down. So we'll move on to trying to factor 42. I notice that 2 can go into 42. And that gives me 21. 21 is divisible by 3, which gives me a 7. So the factors of 42 are 2, 3, and 7. Once we have both numbers broken down into their prime factors, we look to see what factors they have in common. So 42 has a 2, and 56 also has a 2. 56 and 42 share a 7. They don't share anything else though. 56 has 2 more 2's, but 42 only has the 1, and 42 has a 3, but 56 doesn't. So the two factors that 56 and 42 share are 2 and 7. That means that the greatest common factor between 56 and 42 is whatever 2 times 7 is, 14. 14 is the biggest number that will go into both 56 and 42. Now that we've reviewed finding the greatest common factor for numbers, we're going to look at finding the greatest common factor between polynomial terms. I think this is actually easier than finding the greatest common factor for numbers. I'd like to find the greatest common factor between 9x squared y cubed and 6x squared y. We'll start out the same way that we did before, taking one of my terms and listing all of its factors. So 9x squared y cubed. The factors here are 3 times 3 for the 9, and then x, x, and 3 y's. Now we'll go ahead and list all of the factors for 6x squared y. 6 factors into 2 and 3. X squared is x, and then there's 1y. Now we look to see what they have in common. There's a 3 in both of them. There are 2 x's in both of them, and each one has at least one y. That makes my greatest common factor 3x, x, y, or 3x squared y when we put them all together. It's entirely possible that you could go straight from looking at these two terms to writing down the greatest common factor here. Notice that between 9 and 6, the only number that goes into both of them is 3. Between x squared and x squared, we ended up with an x squared, since they both had an x squared. When I look at the y variables, y cubed and y, this one only has one y, which means that even though this one has 3, they only have one y in common, and I only ended up with one y in my greatest common factor. The real goal of finding the greatest common factor is so that we can factor it out, or undistribute it, to get an equivalent expression. For example, let's go ahead and factor out the greatest common factor from the expression 9x squared y cubed plus 6x squared y. We've already determined that the greatest common factor is 3x squared y. What's left of the 9x squared y cubed when we remove the 3x squared y? Looking back in our notes, we can see that if I remove the 3, the x squared, and a single y from 9x squared y cubed, I'll be left with 3 and y squared. So I write that down right here, 3y squared. Then I go ahead and ask myself, from the 6x squared y, what's left when I remove 3x squared y? And the answer is, we'll be left with 2, no x's, and no y's. I might write this down a little bit more concisely as 3x squared y multiplied by 3y squared plus 2. Notice that if I multiplied this back out, and I took the 3x squared y multiplied by 3y squared, and then multiplied it by 2, I would end up with exactly the same thing that I started with. So it's an equivalent expression. It's just two ways of writing down the same thing. This is great because it means that you have a way to check any factorization. You can always multiply it back out and see if you get what you started with. That'll mean that your factorization is correct. All right, it's your turn to try some of these problems now. I've got 3 problems of varying difficulty. I'd like you to try factoring out the greatest common factor. And then, once you have an answer, go ahead and multiply it back out to see if you get what you started with and check your answer. Are you ready? Go ahead and pause the video now and give these problems a try. And we're back. Let's go ahead and take a look at these problems together. My first example is 8y squared plus 4y. Now our first step is to figure out what the greatest common factor is. I start by looking at the two numbers, 8 and 4. What's the biggest number that they both have in common? That'll be 4. Between y squared and y, what's the biggest number of y's that they both have in common? That'll be just one y, because the 4y has only 1, even though the 8y squared has 2. So my greatest common factor is 4y. My next step is to factor that greatest common factor out of both terms. So I write a 4y on the outside, and then I write down what's left when I remove it from each of those terms. If I take a 4 and a y out of 8y squared, I'm left with a 2 from the 8 and a single y. If I take a 4y away from 4y, I'm not left with really much of anything, except that I need a 1 as a placeholder, so that when I go to multiply everything back out, I'll be able to get back where I started. That leads to my last step, which is the check. I'm going to go ahead and multiply this expression back out to see if I get what I started with. 4y distributed to my two pieces in here becomes 4y times 2y plus 4y times 1, which simplifies to 8y squared plus 4y. So sure enough, this is a correct factorization. Notice that I really do need that placeholder 1 so that when I multiply the 4y back out, I get back to what I started with. Now let's look at the second example. Here I had 24x squared minus 6x cubed plus 18x to the fourth. To find the greatest common factor, I decided to go ahead and write down all of the factors for each term so that I could visually see what they have in common. 24x squared is 2 times 2 times 2 times 3 times x times x. Negative 6x cubed is a negative 2 times 3 times x times x times x. And 18x to the fourth is a 2, a 3, a 3, and 4 x's. Now that I have all of the factors listed, I can visually check to see which ones they have in common. It looks like every single one of these 3 has a 2, each one has a 3, and each one has 2 x's. But that's all that they have in common. That makes my greatest common factor 2 times 3 times x, or 6x squared. Now that we know what the greatest common factor is, we're going to try to factor it out of those terms. So I start by writing my greatest common factor on the outside, 6x squared, Then I put some parentheses and fill it in with whatever's left when I remove the 6x squared. So if I remove 6x squared from 24x squared, I'm left with 2 times 2, or just 4. When I remove 6x squared from negative 6x cubed, I still have a negative sign, and I have one single x. When I remove 6x squared from 18x to the 4th, you can see that I'm left with a 3 and 2 x's, or 3x squared. Before we move on to the check, I want to point out something about that negative sign. My original term had a negative 6x cubed. That negative is important. You need to keep track of it. I kept track of it by writing it in here so that I would see it again when I went to write down what was left over, the negative and the x. You can also think of that as a negative 1 if you want to. If you have lost a sign somewhere though, your check will help you figure it out. So let's go ahead and do that now. I check by multiplying this back out. 6x squared multiplied by 4 is positive 24x squared, which is what I wanted. 6x squared multiplied by negative x will give me that negative 6x cubed, which is what I needed here. And then 6x squared multiplied by 3x squared is 18x to the 4th. So looks like we got it. That factorization works. Finally, let's take a look at this last example. Here I had 7x to the 5th y squared plus 14x squared y cubed minus 7x y to the 4th. My first task is to find the greatest common factor. On this problem, I chose to find the greatest common factor by looking at each term to see what they had in common. But don't be afraid to make this list like we did over here so that you can really visually see what all of the factors are and which ones they have in common. I suspect that the more often you do that, make the list, see what they have in common, the easier it will be to see what they're going to have in common before you actually write everything down. Looking at these 3 terms, I started by looking to see what the numbers have in common. I have a 7, a 14, and a negative 7. What they all have in common is just 7. Now I take a look at the x's. I have an x to the 5th, an x squared, and a single x. Because this last term has only a single x, that's all that's going to make it into my greatest common factor. Because remember, I need things that they all have in common. Next I look at the y's. I have a y squared, a y to the 6th, and a y to the 4th. That's like saying this term has 2 y's, this one has 6, and this one has 4. So the greatest amount that they have in common is 2, which makes my greatest common factor have a y squared. So altogether, my greatest common factor is 7xy squared. Now that we've found the greatest common factor, our task is to factor it out. So I start by writing my greatest common factor, 7xy squared, on the outside of a set of parentheses. On the inside, I'm going to write down whatever is left over once I remove the greatest common factor. From 7x to the 5th y squared, when I remove a 7, an x, and a y squared, all that's left is 4 x's from the x to the 5th. In 14x squared y to the 6th, when I remove a 7, I'm left with a 2 from the 14. When I remove a single x, I'm left with a single x from the x squared. And when I remove 2 y's, I'm left with 4 y's from the y to the 6th. With the negative 7x y to the 4th, when I remove a 7, I still have a negative. When I remove an x, there's no more x's left. And when I remove a y squared, I'm left with 2 y's from the y to the 4th. Lastly, I'll go ahead and check my factorization by multiplying it back out. 7xy squared multiplied by x to the 4th is 7x to the 5th y squared. When I multiply by 2x y to the 4th, I get my 14x squared y to the 6th. And notice that when I multiply by negative y squared, I get that negative sign back that I needed on the last term, which gives me negative 7x y to the 4th. So sure enough, when I multiply it back out, I get the same thing that I started with, which means that this is a correct factorization. When you first start factoring, it can be difficult to see what the greatest common factor is. So don't be afraid to go ahead and write down all of the factors for each term like we did over here, so that you can really see what the greatest common factor is and what's left over when you take it out. The more you practice, the easier it will get to see that greatest common factor, so just keep practicing. Our next topic is factoring by grouping, which is a skill that we're going to use really heavily in the next section. Before I tell you how to do factoring by grouping, I'm going to walk us through an example together, and then we'll write down the steps for this process. My example starts with 5 times x plus y plus 2x times x plus y. Let's start by identifying the two terms in this expression. Remember that terms are things that are being added or subtracted. So in this expression, one of my terms is 5 times x plus y, and my other term is 2x times x plus y. Within each of those terms, there are some factors. So we're going to take each term and break it down into its factors. For 5 times x plus y, the two things that are being multiplied together are 5 and that thing x plus y. In 2x times x plus y, the three things actually that are being multiplied together are 2x and x plus y. Let's go ahead and look at that list of factors and see if they have anything in common. My first term had a 5 and an x plus y. My second term had a 2 and x and an x plus y. They both have an x plus y, which I'm going to highlight in pink and think of as that pink thing. So the factor that they have in common is x plus y, or that pink thing. To write this in its factored form, I take out the greatest common factor, which is that pink thing. Then I put some parentheses and see what was left after I removed the greatest common factor. For my first term, if I take out that pink thing, I'm left with a 5. And in my second term, if I take out that pink thing, I have a 2 and an x left over. So my factored form then is x plus y multiplied by 5 plus 2x. Factoring by grouping is a technique to try when there's no common factors in the terms and the polynomial has exactly 4 terms. So for instance, this polynomial is a good candidate. The terms have nothing in common and there are exactly 4 of them. When factoring by grouping, the first step is to group the terms into 2 pairs. So I'm going to group these first 2 terms together as y cubed plus 6y squared, and then I'm going to group my second 2 terms together as 4y plus 24. Now that we've grouped the terms into 2 pairs, we factor each group. So in y cubed plus 6y squared, the 2 terms have a y squared in common. So I factor out a y squared, which leaves me with a single y left behind, and a 6. So I have y squared times y plus 6. Now I look at my second group, 4y plus 24. I see that they have a 4 in common. So I'm going to factor out a positive 4. I'm left with y plus 6. When I factored each of those pairs, I was left with a y plus 6 in each of them. So these 2 terms have a y plus 6 in common, which I can factor out. When I factor out the y plus 6, I'll be left with y plus 6, and what's left inside is a y squared from the first term and a 4 from the second term. So there's my final factorization. Y plus 6 multiplied by y squared plus 4. While we're at it, let's go ahead and check that if I multiply this back out, I'll get back to what I started with. So I'll take my y plus 6 and multiply it with y squared plus 4. Notice that I'm going to need to FOIL to multiply this out. I have y times y squared is y cubed, y times 4 is 4y, 6 times y squared is 6y squared, and 6 times 4 is 24. Now my terms ended up in a different order, but they're exactly the same as the terms that I started with, which tells me that this is indeed a correct factorization. Finally, I want to point out that the order of the factors doesn't matter. I mean, which ones you group together doesn't matter for your final answer, as long as you start with 4 terms and make 2 groups. Go ahead and try it yourself if you want. Rearrange these terms, group them however you want, and you'll end up with the same factorization in the end. Now, whenever you're factoring, but especially when you're factoring by grouping, it's important to be able to notice when things go wrong. So we're going to take this polynomial, which looks like a good candidate for factoring by grouping, try factoring it, and notice what goes wrong. Now, this polynomial does look like it might be able to be factored by grouping. I've got 4 terms, and they don't have anything in common, so we're in the right starting place. My next step is to go ahead and group my terms. So I'm going to group the x cubed with the 3x squared, and then I'm going to group the negative 5x with the negative 5. Then I start trying to factor things out of my group. I've got x cubed plus 3x squared. They have an x squared in common, so I'll factor out the x squared, which leaves behind a single x from the first term and a 3 from the second term. In my next pair, I see that I've got a negative 5 in both terms, so I'm going to factor out a negative 5, which leaves me with an x in the first term and a 1, remember that placeholder 1 that we need, from the second term. So far so good. We haven't done anything wrong. But now when I stop and look at it, I see that these two aren't the same. My first term has an x squared multiplied by an x plus 3. My second term is a negative 5 multiplied by x plus 1. These don't have anything in common. Because my two terms don't have anything in common, I can't factor anything out, so my factoring by grouping process is broken down. In fact, it turns out that there's just no good way to factor this polynomial. Polynomials that don't factor nicely have a special name. We call them prime polynomials. You can think of them as being like prime numbers, numbers that can't be factored any further. Now, the real point of this example is that when you're trying to factor by grouping, and you find that after you factor things out of your two groups, you're left with stuff that's not the same, either something has gone terribly wrong in your factoring, or the polynomial just doesn't factor, and that's okay. Don't try to keep going. Stop, write down that it's a prime polynomial, and move on. Or maybe go back and look at your work and see if maybe there was a small mistake that you made somewhere. Okay, now it's your turn. Here are two expressions that I'd like you to try factoring by grouping, and I promise that they both do actually factor. So go ahead and pause the video, give it your best shot, and then we'll come back and talk about them. And we're back. Let's go ahead and see how factoring by grouping is going. In my first expression, I have x plus y plus 2y minus 5x minus 10. So I decided to group the first two terms together, xy plus 2y, and the second two terms together, negative 5x minus 10. The first two terms have a y in common, so I factored that out, which left me with x and 2. The second two terms have a negative 5 in common, so I pulled that negative 5 out. When I take negative 5 away from negative 5x, I'm left with a single x. When I take a negative 5 out of negative 10, I'm left with a positive 2. Notice that if I multiplied this little guy back out, I would get back to where I started. Now I can take a big step back, look and see if anything good has happened. I have y times x plus 2 and negative 5 times x plus 2. These guys have an x plus 2 in common, so I can factor the x plus 2 out. So I go ahead and write down my x plus 2 factor. When I take the x plus 2 out of my first term, I'm left with a single y. And when I take the x plus 2 out of my second term, I'm left with a single negative 5. So my final factorization is x plus 2 times y minus 5. And remember that you can check that by multiplying this back out. Notice that I get the same terms, even though they're in a slightly different order than the original. My second example is a squared b squared plus a squared minus 3b squared minus 3. I paired the first two terms together, a squared b squared plus a squared, and the last two terms together, negative 3b squared minus 3. From the first two terms, I'm able to factor out an a squared, since they both have an a squared in them. Now, when I remove an a squared from a squared b squared, I'm left with a b squared. When I remove an a squared from a squared, there's not really anything left over, but I need a 1 as a placeholder, so that if I multiplied things back out, I would get back to where I started. In my second grouping, I've got negative 3b squared minus 3, and both of these terms have a negative 3 in them. So I take out a negative 3, which leaves me with a b squared, and again, a plus 1 as a placeholder. Now I pause, take a deep breath, step back, and look at what I have. I have a squared times b squared plus 1, and negative 3 times b squared plus 1. They both have a b squared plus 1 object in them. So So I can factor that b squared plus 1 all the way out. When I do that, I'm left with an a squared from the first term and a negative 3 from the second term. So my final answer is b squared plus 1 multiplied by a squared minus 3. And again, I can check by foiling that out and seeing that I do in fact get the same thing that I started with. So all I've done is factor it and change its form a little bit. Don't worry if it takes you a little while to get the hang of factoring up the greatest common factor and then factoring by grouping. The more you practice, the easier it'll get.